And hi, everyone. Today, I'm going to talk about Floquet conformal field theory, which is based on this archive paper and some other works in progress, which is done with my collaborator Yingfei, Xueda, and Ashwin. Okay. Here's my outline. So I'll start with the motivation and then introduce the most general setup and also some conjecture about the general dynamics in the system. Then I will illustrate the main phenomena and the physics with a very concrete example and show you some interesting emergent spatial features in the system. And then I will talk a little bit about the random and also quasi-periodic driving and then close with the outlook. Okay, so our motivation or goal is to engineer some interesting phenomena in these many-body Floquet systems, and we still want the dynamics to be exactly solvable, and so then we choose the 1+1 dimensional conformal field theory as our platform to do the engineering, because of the powerful conformal symmetry. It's the model we design can be like exactly solvable. And also we want our result to be universal and also robust. That gives us some constraint on the driving protocol we should use. And the protocol we come up with turns out to be suitable for starting random and quasi-periodic driving that I'll mention at the end of this talk. And the one thing I want to address is that thermalization is, of course, a very interesting phenomena and concept in non-equilibrium physics, but that's not the thing we are going to talk about in this talk. Okay, and here's the general setup. So the system we choose is a 1+1 dimensional unitary and the rational conformal field theory, which covers pretty much all the system that are realizable in the real in our lab, and the system size is denoted by L, and the boundary condition can be either periodic or open. It doesn't matter. And the driving protocol is implemented by changing the Hamiltonian density periodically in time. So let's say if T naught naught is our Hamiltonian density, then we multiply it by such an envelope function f of t and x. So it has this spatial dependence in space and is periodic in time, like ft plus capital T equals to f of t. Okay, and the reason for this choice is the following. So because we want our result to be universal, and this is by construction like universal and applies for any CFT because the this T naught naught, the stress energy tensor, is definable for any CFT and only involves the Virasoro algebra, so it's universal, and also it's simple to understand because it has a clear physical meaning in terms of the quasi-particle picture, which is believed to be true for any rational conformal field theory, and it's the following. So what this f of t does is it modifies the velocity of the quasi-particle in our system. Let's say we create some excitation which is describable by some quasi-particle, and for the left mover denoted by this blue dot, it will move to the left, but now the velocity will has a space-time dependence which is proportional to this f of t and x. Okay, and for this system, it turns out to be that studying the classical motion of this quasi-particle is sufficiently good to understand the general quantum dynamics. And in particular, we look for the fixed point of this classical motion, meaning that the particle can start from somewhere and come back to the same point after one or several cycles of driving. And we have the following conjecture, is that the existence of such kind of fixed point of the classical motion of quasi-particle is the same as saying that the dynamics is heating. We don't have a general proof, but I will illustrate this with some concrete example later. Okay, but for general FFT, it's still challenging to solve the dynamics for general generic FFT. So we make some further assumption. We assume FFT is a step function in time, and in space, it only has a single Fourier component so that it can be written in this form. And now, with this simplification, And the Hamiltonian now only involves the 3 Virasoro generators. So this A of t will give rise to L naught, and B of t will give rise to L plus and minus n. And this forms a subalgebra of the full conformal Virasoro algebra, which is isomorphic to this SL2R algebra, for which we have a very well understanding. Okay. And now let's do a concrete example to see what really happens. So this is the general form, and in the following we choose just n equals to 1. So in general, we have, say, 1 plus 1 minus cosine 2 pi on x over L. And n equals to 1, we can write it as 2 times sine squared pi x over L. Okay. And so the system we consider is an open chain with a conformally invariant boundary condition at x equals 0 and x equals to L. And the in each cycle, the Hamiltonian will change between H1 and H0. H1 is the n equals to, is the so-called SSD Hamiltonian, and H1 is our familiar like a Hamiltonian for the general system. And the tuning parameters are T0 over L and T1 over L, which are the time period for which we apply H1 and H0. Okay, so physically what this H1 does is that the quasi-particle can move to the left or to the right with diminishing velocity near the boundary. Okay, and with this concrete model, you can show that in the high frequency regime, there are no fixed point for the quasi-particle motion. And if you calculate the energy profile, you will see that it just keep oscillating in time. So it means the system is having a non-heating dynamics. As we lower the frequency, you can find that there will be 2 fixed points for the quasi-particle, one for the left mover and the other for the right mover. Then the quasi-particles can get accumulated at these 2 fixed points and form 2 energy peaks. If you calculate the total energy, you will find that it exponentially grows with time with the coefficient proportional to central charge. So it's universal for any CFT. So now the system is in the heating phase. And you can further show that whenever you have 2 fixed points, you will find that the system is in the heating phase. So there are one-to-one correspondence between having fixed point and having a heating dynamics. And further, you can show that you can also find some interesting phenomena in the entanglement pattern. Namely, if we calculate the entanglement entropy for a subsystem, and the entanglement will linearly grow with time as long as the subsystem includes one of the 2 energy peaks, and it doesn't grow at all if the system doesn't include any of the peaks. And here the slope of the linear growth also proportional to central charge, which is also universal for any CFT. And you can also show that the total energy of the system and the half system entanglement satisfies this universal relation that is true for both periodic, random, and quasi-periodic driving. And now let's try to understand what happens for general n. So for general n, we just replace that H1, that's SSD Hamiltonian with H sub n. We just put n here. And now this system actually can be understood as an array of n copies of n equals to 1 system, meaning that if you look at the subregion of length L over n, in the subregion, the Hamiltonian looks exactly as we have a H1 like for this subsystem. Okay, so with this, it's quite natural to believe that all the features above still holds in this general n. And indeed, by calculation, you can find that we will have 2 peaks for in each of the subregions. So in total, we will have 2 energy peaks. And you can further show that there will be entanglement for every next nearest neighbor. For every 2 nearest neighbor energy peaks. But if you look at the energy peaks that are next to nearest neighbor with each other, they don't share any entanglement. And this setup also shows the dynamical Casimir effect more clearly, meaning that if you look at the energy density away from the critical point, it actually gets even smaller than the conventional Casimir effect. So without turning on the driving, the Casimir energy is this amount, but with the driving, it will be multiplied by this n squared, so it gets smaller. And in the real lab, noises are inevitable, so it's natural to ask what happens if the driving frequency has some fluctuations denoted by this delta t. And the answer for that is the non-heating phase will immediately disappear, meaning that if we start with the parameters that are deep in the non-heating phase and turn on a little bit fluctuation, you will find that energy grows exponentially with time and then entropy grows linearly with time. And this absence of non-heating phase can be proved rigorously mathematically, which is related to the Furstenberg theorem. And for the heating phase, on the other hand, for the heating phase, you can check that all the spatial features like the energy peaks and the entanglement structure are still robust for moderate fluctuation. Okay, and now we want to ask what happens if it's between periodic and random, namely what happens if we have a quasi-periodic driving, what is the phase diagram? And the answer to this question is the following. So we can map the dynamic, so we can map the operator evolution to a one-dimensional quasi-crystal by the transfer matrix method, meaning the transfer matrix method, the transfer matrix for the wave function can be mapped to the operator evolution in the CFT side. So on this side, it's quasi-crystal, this side is the quasi-periodic driving CFT. So if we have on this side, if we find the system have bands, it means the CFT is in the non-heating phase. And if on this side, we don't have any bands, meaning the system is localized, means that the CFT is having a heating dynamics. And our experience with the quasi-crystal immediately tells us the existence of a non-heating phase actually depends on the realization of the quasi-periodicity. For example, if we use the Fibonacci type of quasi-periodicity, we won't be able to find any measure non-zero. We won't be able to find a lot of we won't be able to find a non-heating phase. And now I'll just close with this summary and some outlook. So this system provides a tool to realize a very robust energy and entanglement pattern in the heating phase. Namely, we have EPR pairs accumulating at the two energy peaks, and it might be useful for quantum computation. And it's interesting to solve the problem for generic FFT and also for higher dimension, and also interesting to consider some holographic interpretation. With that, I will thank you for your attention.